This explainer follows a proof that builds a transition rule on a small toroidal lattice while keeping every computed quantity as an exact rational number. The central idea is to replace operations that usually need square roots, exponentials, or floating point approximations with algebraic steps that can be checked exactly. The video will connect the geometric scoring rule, the sparse probability projection, and the asymmetric pump layer into one proof of a rational, row-stochastic, sparse transition kernel. The first step is to understand why exact rational arithmetic matters for this construction. Exact rational arithmetic means that every stored number is a fraction of two integers, so addition, subtraction, multiplication, division by a non-zero number, comparison, and taking the larger of a number and zero all stay inside the same number system. This closure property is the backbone of the proof, because if every input is rational and every operation preserves rationality, then the final transition probabilities are reproducible without floating point rounding drift. The lattice in the proof has 64 states, arranged as triples of residues modulo 4, and each state carries a rational unit quaternion, which is a four-number object whose squared coordinates add to 1. The scalar coordinate of each quaternion is assumed to stay between two positive bounds below 1, and this annular condition prevents divisions by 0 while also avoiding extreme temperature values later in the construction. The geometric step sends each quaternion to a point on the positive sheet of a hyperboloid by dividing the vector with first coordinate 1 and the three spatial coordinates by the quaternion scalar coordinate. This lift is rational because every coordinate is a rational number divided by a non-zero rational number, and it lands on the hyperboloid because the Minkowski self-product equals 1 after the unit quaternion identity is substituted. The hyperboloid model represents hyperbolic geometry using the Minkowski product, which subtracts the ordinary dot product of the spatial coordinates from the product of the first coordinates. Instead of computing the actual hyperbolic distance, which would require an inverse hyperbolic cosine, the proof uses hyperbolic quadrants, defined as the square of the Minkowski product between two lifted points minus 1. This quadrant is rational because it is built from rational products, sums, and a square, and it is symmetric because swapping the two lifted points does not change their Minkowski product. The quadrant is non-negative because lifted points on the positive hyperboloid have Minkowski product at least 1, so its square minus 1 cannot be negative. The quadrant separates points because it equals 0 exactly when the lifted points have Minkowski product 1, which in this setup happens exactly when the original rational quaternions are the same. The construction then turns geometry into scores, called logits, by taking negative inverse temperature times quadrants and subtracting a rational torsional resistance penalty. The inverse temperature is the scalar expression 1 minus the quaternion scalar coordinate, divided by that scalar coordinate, so it is rational and bounded because the scalar coordinate stays inside the annulus. Each logit is therefore rational, since it combines rational quadrants, rational inverse temperature, rational attenuation strength, and rational resistance using only field arithmetic. A probability row must have non-negative entries that sum to 1, and the proof obtains such a row by applying Sparsemax to the rational logit vector. Sparsemax is the Euclidean projection of a score vector onto the probability simplex, meaning it finds the nearest vector whose entries are non-negative and whose total is 1. The key closed form says that each Sparsemax entry is the positive part of its logit minus a threshold, where the threshold is chosen so that all positive parts add up to 1. For the active set of entries above the threshold equals the sum of their logits minus 1 divided by the number of active entries. Because the active set is found by exact comparisons of rational logits, and because its threshold is a rational sum divided by an integer, every Sparsemax probability is rational. Sparsemax also gives exact sparsity because any logit at or below the threshold receives probability exactly 0, rather than a tiny positive weight. The row is guaranteed to have support because the Sparsemax entries sum to 1, and the self-loop is always among the largest logits because its quadrants and resistance are 0, while all other penalties are non-negative. At this point, the proof has a rational sparse row-stochastic kernel, where row-stochastic means that every row contains non-negative transition probabilities adding to 1. The pump layer begins with a symmetric rational base walk on the supported edges using weights that are the same in both directions along an undirected edge. For this base walk, the stationary reference weight of a state is proportional to its total incident weight, and detailed balance holds because the flow from one state to another equals the flow back along the same edge. Detailed balance means that, under the reference distribution, every edge carries equal probability flow in both directions, so the base walk has no preferred circulation. The reverse valve breaks this symmetry by multiplying reverse direction transition mass by 1/1 plus attenuation strength times resistance, a rational factor between 0 and 1. The mass removed from each reverse transition is added back to the self-loop, so each row still sums to 1 even after the reverse movement is weakened. All entries of the valve-modified kernel remain rational because the base probabilities, valve factors, and return diagonal masses are rational combinations of rational numbers. For a supported forward edge, the base referenced current equals the forward flow minus the reverse flow after valve attenuation. Using the detailed balance identity of the symmetric base walk, this current simplifies to the edge weight divided by the total degree weight, multiplied by 1 minus the reverse valve factor. That expression is non-negative because the weight is non-negative and the valve factor is at most 1, and it is strictly positive when the edge has positive weight and the reverse valve truly attenuates. This proves that the modified kernel breaks detailed balance with respect to the base reference measure whenever at least one supported forward edge has non-zero weight and non-trivial reverse resistance. The proof is careful about scope because it establishes a base-referenced forward current, not a full proof that the modified kernel has non-zero circulation under its own stationary distribution. The parity safety claim follows from the same rational closure argument, since canonical reduced fractions are unique and therefore two machines with the same starting data compute identical rows bit for bit. The annular stability claim follows because the inverse temperature function decreases continuously on the allowed scalar interval, keeping the system away from both collapse into a single move and completely flat diffusion. The complete proof therefore succeeds as an exact executable construction. The lift, quadrants, logits, Sparsemax row, base walk, reverse valve, and pump kernel all remain rational. The rows are stochastic and sparse, and the valve creates a non-negative base-referenced forward current.